So here we're going to look at some examples for substitution and elimination, and we're going to have to decide the mechanism that these are going through. Now remember the general way is to first look at our alkyl halide, identify as primary, secondary, tertiary. Then we look at our reagent. Is it a base, nucleophile, both, strong, weak, bulky, things like that. And then last I like to look at the conditions such as the solvent and the temperature. The reason why we like to look at the alkyl halide first, so here we have our alpha position, the one bonded to the leaving group, that is primary. By understanding it's a primary alkyl halide, we can limit our choices to SN2 and E2. Because we can't form a carbocation on a primary position, we can't do SN1 or E1. Next, we look at our reagent. It is a strong base, and more importantly, it is bulky. This terbutoxide is sterically hindered and cannot do substitution. So what it's going to do instead is remove a hydrogen from the beta position. The beta is the carbon bonded to the alpha. You could have multiple beta positions, but on a primary alkyl halide there's only one. And I'm going to remove that hydrogen, form a double bond, kick out my chlorine, and we get that alkene. On the right, we have a primary alkyl halide again, alpha position here. We can do either E2 or SN2. And so looking at our reagent here, that is a strong nucleophile. It is a nucleophile because it is sulfur. Sulfur does not act as a good base, so we can eliminate the E2 process, and this is going to be SN2. Now they didn't have to show the solvent, but the solvent agrees as well because that's an aprotic solvent, favoring SN2 and E2. But again, the nucleophile here is going to make us identify this as SN2 and not E2. And so this is going to be a concerted process where our nucleophile adds to our alpha carbon, kicking out the leaving group. So we're going to redraw this, but instead of the chlorine we have the sulfur, and the CH3 is still attached. Keep in mind the metals are just spectators. They should not be in my product. The sulfur, like oxygen, likes to have two bonds. It's currently bonded to carbon here, and we're forming a new bond to this alpha carbon there. Next, we have a secondary alkyl halide. These ones get tricky because all four are possible: SN1, SN2, E1, E2. So we need to look at our reagent. This is a strong base, and it's also a small base, which is important. Now, the heat also helps us identify this as an elimination. Sometimes nitrogens can be nucleophiles, but the fact that we're heating this up kind of is letting us know more it's elimination. Because we have sodium here, spectator ion, positive charge, we know this is a strong base, something with a negative charge. Because it's small, we would expect the Zaitsev product, which is eliminating to the more substituted beta position. However, the hydrogen and the bromine are both dashes. In order to do an E2 elimination, we need to have the hydrogen anti-periplanar or anti-coplanar, however you want to describe it, to the leaving group. So if the bromine in the ring is a dash, the hydrogen has to be a wedge. Well, the favored position is actually not possible because the hydrogen's not correct. So we look at the other beta position down here. This beta position relative to our, again, alpha position, the carbon with the leaving group, we have two hydrogens. One of them is in the correct position. One of them is anti-coplanar or anti-periplanar to the bromine. So we can do E2 elimination there, in which case we will form our double bond there. Whoops, I went the wrong way on that one. That was a rookie mistake. We go to the hydrogen. The hydrogen forms the double bond, and we kick out our leaving group. Now up here we did not do anything to this beta carbon, so it's going to maintain its stereochemistry. Had we used a weaker base and did an E1 reaction, we would have favored the Zaitsev product, the more substituted alkene, which would have been this product. But because we did an E2, we are going to favor this product here. So that was an E2 mechanism. Same thing over here. We're going to do another E2 mechanism. We have a secondary alkyl halide. We are adding a strong base and adding heat as well. We cannot eliminate in this beta position because there's no hydrogens. This beta position has hydrogens. So we can eliminate towards that direction, and this would be our product. I'm not going to draw all three hydrogens, but there's a hydrogen there. Deprotonate, kick out our leaving group. Next, we have methanol, but that's getting ahead of ourselves. Forgot to mention we have a secondary alkyl halide. We are possibly going to do an SN1, SN2, E1, or E2, but we look at our reagent. It is weak, meaning that we're going to wait for the leaving group to leave. Our nucleophile slash base is not strong enough to react first, so we're going to form a carbocation. With that being said, we're going to go through the E1 or SN1 process. Because we're adding heat, that's going to favor the E1. If I did not add heat, I would expect the substitution to occur, the SN1. But because we're adding heat, we're going to get the E1 elimination product. So initially what happens is we lose our leaving group to form a carbocation. Now that is a secondary carbocation. We have these positions over here that are tertiary. We could potentially do a hydride shift rearrangement to get a new carbocation in a tertiary position. Now, if we did substitution SN1, our alcohol would add here as opposed to where the initial carbocation formed. Now when we do our elimination, we can do one of two things. We could eliminate this direction, or we can eliminate this direction. Both of those are possible. Notice that I didn't do anything with this carbon up here, so that stereochemistry is going to stay the same. It's always going to be a dash. Now another thing I could have done is when I did my shift, I could have shifted from the other side, in which case I would have had my carbocation right there. And if that were to happen, I would have gotten this product and this product. Now, why did I eliminate in the ring, within the ring, and not out towards the methyl group in either of those scenarios? Again, that's because we did E1, which is a Zaitsev favoring mechanism. We're going to get the more substituted alkene. And all the alkenes I drew are tri-substituted. They have 3 carbons attached to the double bond. So all of these are different stereoisomers or regioisomers, constitutional isomers of the product. So all 4 of those are potentially possible, and I don't think one of those would technically be favored over the other. So let's look at the last one, and to do that I'm going to clear up some space here. So now that I got some space here, let's go ahead and do the last example. We're going to add excess NaNH2, which again is a strong base. We have these secondary positions, and that means we can do, anything really, but because we have a strong base, we're going to do E2. Now also, notice that these two carbons have leaving groups attached. They each have leaving groups. These chlorines are said to be vicinal. They are on adjacent carbons. And whenever you have a dihalide, a vicinal dihalide, you could potentially do an elimination twice to give you a triple bond. Now, if we used a bulkier base, it's possible that we could eliminate the opposite directions to the Hoffman products for each and get this conjugated diene. But because we're using a smaller base, the sodium amide, NaNH2, we're actually going to favor the Zaitsev-like product, which is the elimination towards the center, the more substituted alkene. And so when you add your first equivalent, we're actually going to get a double bond here, like this. And one of those chlorines would still be present. In other words, we have our hydrogen, and our base is going to remove the hydrogen, form a double bond, kicking out the chlorine. Now excess just means that we have an excess of our base. So the second equivalent of the base is going to remove this hydrogen that is here, form another pi bond, and kick out our other leaving group. Therefore, our product would be a triple bond. So those are some examples of SN1, SN2, E1, and E2. We really didn't see an SN1 mechanism in there for this one, but if you watch some of the other videos, you might see some of those. There should be about 2 more videos in this playlist that contain differentiating between the mechanisms when you see various reagents.